Okay, so let me record the lecture number 3. This is number 3, part 1, part A. And let's go. I will start with the problem. A problem, just to show you how we can solve those problems from the braces. So, problem. Problem. So, suppose E is an infinite dimensional Banach space show that the weak topology, is not metrizable. Okay, solution. Suppose for contradiction. That there exists a metric call it D from E times E, generating this weak topology, this is signal. Let me write this is the weak topology, so I can write it down using the notation that we introduced. In particular, for any k belonging to n, so those are natural numbers, I can consider just the ball with respect to this matrix, center at 0, of radius 1k. For any k, the set, and I put here bk by the definition, which is equal to the set of all x's belonging to E, satisfying the condition that distance, and here I put here 0, x is smaller than k, is open, by definition, because it generates this matrix, is open in sigma E star topology. So, in such a case, there exists a neighborhood, there exists a basic weak neighborhood of 0, and put it like this, V, and I put here F epsilon. So let me write it down. What is the Vk? Maybe I write it down. Epsilon k, such that Fk. No, let me write it down. This will be like a F1k, F2k, blah blah blah, Fnk. This is a finite set which is contained in E star and epsilon k is larger than 0, such that this v f k epsilon k is contained in this bk. Is contained in this bk. So great. So we got something. So what else do we get? What else do we get? Okay, so suppose now. That G belongs to the E star is an arbitrary element there. So that means in certain way, it means we're going to use this arbitrary for every G belonging to E star. So it's a big quantifier, and it will allow us to make a statement about an arbitrary. Okay. Since by the definition of the weak topology, G is weakly continuous, and that means that G minus 1, and I put here minus 1, 1, call this set, okay, I call this U, is weakly open. Neighborhood. Of 0. Therefore, since we have this matrix, that means there exists a k larger, okay, k belonging to n such that bk is contained in G minus 1 minus 1, 1, and that one of course contains V F K epsilon k. I have these two inclusions, V F epsilon k. Very good. So let me continue. So let me check something, because I forgot which one of the assignment problems actually is. Okay, you will know it. It's actually using this property. So what does it mean? This in this case, what does it mean? Here, of course, if you notice, the properties here is simply that if you have here that this Vk belongs there, so it means that that there exists a k belonging to Fn such that for every okay, x belonging to V, and this will be like this, f of k epsilon k, we have here that the G on x is smaller than 1. So that basically means that, so it means this one. That means this one, satisfied. And here, what is the meaning here? So that means input. So that V F K epsilon k. Let's recall this is the set of all x's such that I have here for every f belonging to f k, I have here f, and this is x, is smaller than epsilon k. Smaller than epsilon k. Very good. Very good. But what we know about this neighborhood is that, look, that this neighborhood contains the intersection of k's, so maybe like this, of f belonging to fk, kernel of f. And that was on one of the assignments, on the class. No, this is actually the assignment that you are doing now. So this is assignment, I believe, 7. So in such a case, you just need to show that one. And since the function, so that means, let's write it down, if x belongs to this f belonging to f, k, kernel of f, so that implies that, this implies in particular that g of x is smaller than 1, and since that's a linear subspace, this is a linear subspace, so linear functional is bounded on the linear subspace if it is 0. There is no other way. The g of transform a linear subspace either to whole R or just to 0. The fact is that any linear transformation takes a linear subspace into a linear subspace. So if the linear subspace is bounded, it must be 0. So in such a case, that implies, of course, that g of x is equal to 0. And that, in particular, implies that x belongs to the kernel of g. And we are arriving to another statement, which was on the assignment 6. And this statement simply tells you that in such a case, therefore, G is belonging to the span of Fk. That means it can be expressed, so G can be written as a linear combination of the of the vectors. That's of this f1k, f2k, and this is fnkk, of these functionals. Very good. I don't say this is a unique, they are linear independent. It may be not a unique linear combination, but it can be written. So put, and I put here like this, b tilde. Maybe I should change the symbol. I should write it down as h. Like this, h tilde. So by the definition is the set of all k belonging to n, and I put here fk. So we just proved that the space E star, because we said for every g, this was written for every g, this is true to some kind of a k, so we maybe let me write it down. So we just prove it here that for every g belonging to E star, there exists a k belonging to n such that g belongs to the span of fk. So in such a case, we can just simply rewrite it down that this is contained in the span of this set H tilde. Very good. On the other hand, as we know, from any set of vectors, it is always possible to choose the maximal linearly independent subset. On the other hand, we can choose from H tilde a maximal linearly independent subset, and I call this subset now H, which is nothing else than a Hamel basis of E star. Yes, it's a Hamel basis. The maximum linear independence rate will be a basis. Hamel basis. But this is a contradiction. Because what do we know? Because E star is also infinite dimensional. Banach space so any Hamel basis of E star cannot be countable. Cannot be countable. If it cannot countable, and this contradicts, the fact that H is countable. Of course it's countable, because the H is a union. So H is a subset of a union of the finite set, so it is a countable. So H is a subset of a union of a countable union of finite sets Fk, so H is countable. So, contradiction. So we proved by contradiction that this cannot be metrizable. So I hope that problem is nice, okay, let's say, kind of a problem that shows you that all kinds of the problems that we did in this class actually serve each other, and we can use these facts in other proofs. So please draw a conclusion that doing a problem, the technical problem, sometimes should be considered just as a learning process, learning a technique, a new technique, and this technique may later turn out to be useful in other problems. So let's move to the next topic, and our next topic will be just simply the U-weak topology. So let's start with we'll call it the star weak. Maybe I should capitalize weak topology star weak. This is called star weak topology, and we will use this notation for this topology. So this will be topology. This is the target space, so this is E star, and here we'll put it E. So recall, the duality map that is defined by the formula, namely J, that goes from E and it goes to the E double star, is the map which is defined like that. So put it like this, by the definition is a functional. I will associate this X belonging to E, and this functional will go from E star to R, and will be given that this phi X on F will be nothing else than F on X. So that's how it is defined. This functional is defined by this particular. So we know that this functional is an isometric embedding. This is J is isometric embedding means puts isometric transformation, put it like this. Isometric linear transformation of E onto a closed subspace of E star, double star. So it is possible to identify E with this subspace J of E contained in E double star. So in particular, by using this identification, we can write simply that E is contained in E double star. In general, these two spaces may be different, but let me recall E is called reflexive if exactly this inclusion is actually not an inclusion but equality. But if E is not reflexive, then we will have that this is actually not equal to the E double star. So one more thing. Of course, we already have a weak topology. Notice that we already have a weak topology. And this will be sigma E star, and this will be weak topology because the dual of E star is the double star. So this is regular weak topology on E star. So this is weak topology. And we will denote, however, we can consider the topology on E star which, instead of being generated by all continuous functionals, that means by the E double star, it will be generated by the E, which is generated by the functionals. Let me put it like this, by the functionals. And I put here phi x, and this will be x belongs to E, so we understand this is functional also. So that means, what does it mean? That means I put here x is star weak, we'll call it star weak topology. So put it in red, the star weak topology on E star is the smallest topology, that makes all the functionals continuous. All the functionals are continuous. So what do we have? So let's write it down. So here I have here the topology. So this will be like a regular topology. So this is E star with the regular topology, strong topology. So this is with the node. So this is strong topology. And then of course we have smaller topology, which we denote it like this. This will be like omega. So this will be weak topology. Again, maybe I should clearly write this is again this one. This is the same space, and this will be weak topology. And then we have even smaller topology because there are less requirements, and this topology, will be weak topology, star. Star weak topology. So let's recall, this will be sigma E, and this will be E star, E double star, and this is sigma E star, E. Is this clear that there's that this one is contained, that we have here this inclusion? Is this clear? We know that how it is if you have here a family of maps, like this is our family of maps, then we know that the basis of the topology are the inverse images under these maps of open sets, and you take the finite intersections of this inverse images. So if you have more maps, then you have more sets. So definitely let's say TW star is smaller. So good. So we have here this tree, and as we probably will notice in the moment, if the space E is not reflexive, they cannot be equal. So we say that it's not reflexive, then these two topologies cannot be equal. However, if they are equal, of course, this E is equal to E star, which means reflexive space. So E is reflexive, that implies they will be equal. So maybe the first observation is that one, so maybe let's make a first observation. So let me change the color, so let's say observation, put it like this, corollary. The weak topology, star weak topology, star weak topology is Hausdorff. Okay, proof. Take F1 different than F2 and suppose the F1 and F2 are those functionals for E double. Since F1 not equal to F2, then there exists an X belonging to E, satisfying the property that F1 of X is not equal to an F2 of X. We can assume, we can choose. For example, the possibility that F1 is smaller. If this other way, this you do the same way. You just replace 1 by 2. Choose the case. And this will be like F1 on X will be smaller than F2 on X, and since they are not equal, I can choose a number alpha. Choose alpha. So for some alpha belonging to R. Then, of course, I noticed that guy, we usually write it down like this. This is phi x on F1, and this will be like a phi x on F2. And then you look at this particular inequality here. This is our inequality. So this inequality, let me write it down. So phi x of F1 smaller than alpha implies that F1 belongs to the set U1 equals phi x minus 1 of minus infinity alpha. And since, by definition, phi x is continuous with respect to sigma E star E, U1 is star weak open. And similarly, phi x of F2 larger than alpha, and that implies that F2 belongs to U2 by the definition equal phi x minus 1 alpha infinity, again is open. So put it like this, omega star open, and U1 intersection U2 clearly is empty, because those two sets are inverse images of two disjoint sets. So we got this proposition. So maybe we should mention, so let us emphasize, so clearly sigma E star E is a topological vector space topology. That means that open sets are invariant under, so there's still open under, you can shift this open set, it's still open, and you can also multiply by non-zero numbers, and it will also mean by scaling you can also get the open sets. And in other words, it makes the operations, the vector space operations, addition and scalar multiplication continuous. This is a topological vector space, and we can choose as the basis the basis of neighborhood. Put it like this: W star neighborhoods of a given functional f0 belonging to E star, this sets. And since in the case of the weak topology I use V, so I will write now U, and now I still use F, I still use epsilon, now, good, and this will be the set of all F belonging to E star. I will explain what is F, such that for every X belonging to F, so finite set, F is a finite set, we have here F minus F0X smaller than epsilon, where F is contained in E is a finite set. It's a finite set, and epsilon is larger than 0. So these are the basic neighborhoods. So these are the basic neighborhoods. And that means. So in other words, the idea that this is a basis of the star weak neighborhoods means in other words, for every omega star open set, you call it like this, U, and F0 belonging to U by openness. So there exists a basic neighborhood, so U, F, epsilon, such that, so let me point out, this is the neighborhood, so of course F0 belongs to that one, so such that F0 belongs to this U, F, epsilon again, and U, F, epsilon is contained in U. So that's what it means, basis of neighborhood. That's what means basis of neighborhood. So maybe let's identify something, namely those functionals, are they maybe? So question is like this. Maybe I formulate it as a proposition. Proposition. So we already know that not every functional on the space E star is the functional phi x. So maybe there are other functionals that are continuous. So let's say like this, let E be a Banach space. Let E be a Banach space. And let me write it clearly, and phi, put it like this, phi from E star to R, be a continuous linear, not correctly, omega star continuous linear functional omega star continuous linear functional. So is it possible that I have a continuous linear functional which is not phi of x? Actually not possible. So let's say like this: the only functionals that are continuous on E star are those which are represented by the vectors x from E. That means then there exists x naught belonging to E such that this phi of x is equal to this phi of x not for every f belonging to E star, phi of f is equal to phi this x naught on f, that means f of x naught. Let's do the proof. So the proof, since phi is omega star continuous, so this is omega star continuous, the set, let's say, okay, phi minus 1 of minus 1, 1 is omega star open. So there exists a omega star basic neighborhood of 0, say u f epsilon, contained in phi minus 1 minus 1 1. So what is this? This one will be, let's denote it just simply like a u. That means so that means you will have here like this: u is equal to the set of all f such that for every x belonging to this finite set f, I have here f because this is 0, f0 is 0, so this would be x smaller than epsilon, smaller epsilon. On the other way, you can write it down. So for every x belonging to f, I have here that phi of x on f is smaller than epsilon. Clearly, phi of x is smaller than, since let's put it like this: kernel phi of x, right? For x, okay, I should write it. Since if x belongs to the kernel phi of x, this implies that phi of x f must be equal to must be equal to 0 smaller than epsilon. So we are getting that intersection of x belonging to f, kernel of phi of x is contained in the set U. That's already something important. But now if you have any point here, so take any point. So take any x belonging to f, and this is kernel of phi of x. So you see that in such a case, Tx also belongs to this intersection. Put it like this. X belongs to f kernel of phi x. Why am I putting these things like that? You see? So that implies that phi of x smaller than 1, and because t is here arbitrary, so that implies that in such a case this must be equal to 0. This must be equal to 0. So we got that kernel, that if x belongs to kernel of, that maybe write it down, if x belongs to f, and then this is kernel of phi x, then this one is contained in the kernel of phi. This is contained in kernel of phi. And here, what do I have? I have the results. This is the same results as we were using before. So if that means phi belongs to the span of phi x, x belongs to f. So put, for clearness, for definiteness, f is equal, for example, x1, x2, xn, and in such a case that will imply so there exist constants c1, c2, cn belonging to R such that phi is equal, and this will be equal, k is equal 1 to n ck phi of xk. So in particular, we have here that phi on any f, for every f belonging to E star, will be the same as sigma ck phi xk, and that one will be f, and I can take this sigma out, so this is k is equal 1 to n, k is equal 1 to n, put here ck, and I put here phi xk f, and that by the definition is k is equal to 1 to n ck, and this is f xk. And then why not to return back with the sigma? So this is the same as f, and I put here sigma on that side, take k is equal 1 to n ck xk. And then I say, wow, call this point x naught, so this will be equal phi x naught, and of course that is nothing else than phi of x naught f, and we are getting that, yes indeed, here, then phi is actually equal to phi of x naught, and we prove it. and we prove it. So maybe let me do one more remark. So similarly to the weak convergence, we can also consider something which is called star weak convergence. So let Fn be a sequence in E star. F0 is also in E star. And okay, point. We say that the sequence Fn converges, maybe use red, converges star weakly to F0 if it is convergent, it is convergent to F0 in this star, in this topology. So that means star weak topology. And we will use notation that we'll write it down that Fn, this is, and here we'll put star to F0. This will be the notation. So let me formulate the proposition. Let us formulate the proposition, and this proposition will be the following. So let Fn be a sequence in E star, and then we have here Xn, I put here like this, be a sequence in E, and then you have here F0 belongs to E star, and then X0 belongs to E. Then we have, and we start like this, A, Fn is star weakly convergent to F0 if and only if for every X belonging to E, we have here Fn of X is convergent to F0 of X. B, if Fn is strongly convergent to F0, then this will imply that Fn is star weakly convergent to F0. C, if Fn is weakly convergent, star weakly convergent to F0, then this will imply that Fn is bounded in E star topology. And D is if you have here that if n is star weakly convergent to F0, and suppose that Xn converges strongly to X0, then we have here that Fn Xn converges to F0 X0. So the proof of this statement is very much similar to the proof that we saw in the last lecture 2. For the weak topology, it requires, it's actually all the same statements, namely, the first one is just the definition of the convergence, so that one follows from the definition. That one is easy because the topology is stronger, so this is obvious. The strong topology is stronger, so then, and that one is from the uniform boundedness principle. And the last one is one can figure it out in a clear way. So maybe I will do the last one just for the purpose of being complete. So let's do the last one. So I put it like this: absolute value fn xn minus, and this will be f0 x0. So I will actually rewrite it down a little differently. I write it down. This is fn minus f0 x0. So that gives me this one. So I put here like this: minus fn x naught and minus fn xn, closure. So this is the same. See, these two things cancel. That one cancels with that one, and what I'm getting is actually plus. So that must be just simply plus. This must be plus. Now I'm getting the same. So this is very much the same. So I can continue. So rewrite it down. This will be like this: fn minus f0 x0 and minus plus. I put here like this: fn, and this will be xn minus x0. Okay, so now I keep this first one unchanged, and that one I change to the norm of fn, and this one will be xn minus x0. So I notice, so this goes to 0 as n goes to infinity, because that's the definition of omega star convergence. But that was our assumption. That one is bounded. So I can say this is smaller than a certain number r. And this one goes to 0 as n goes to infinity, because that's the convergence in strong topology, so everything goes to 0. Everything goes to 0. And maybe this is the good moment to stop, and we'll continue in a moment with the other with the further material.